Hi everybody, 11 Institute welcomes all the students of Standard 10 to the subject Science, chapter number 11, video lecture number 7. In the previous video lectures, we have seen about atmospheric refraction and several phenomena like twinkling of stars, the early sunrise and delayed sunset occurring due to the effect of atmospheric refraction. In today's video lecture, we are going to study about a new topic, that is scattering of light. So before jumping into the topic, I will show you some examples, some phenomena and what actually happens in scattering of light. So basically in scattering of light, suppose there is a particle over here and a white light is incident on it, and now this white light is split into different directions. These splitting of light, right, due to this small particle is known as scattering of light. Means the path of the light becomes visible after striking this particle. So this visibility of the path of light is known as scattering of light. Let us see a few examples which will make it quite clear. Right, you see the sky color is blue. Actually there is no color of sky, right? Actually the sky is black in color, or we can say it does not have any color. But when seen from earth, the sky is blue in color. We very well know this, right? The sky is blue in color. Now why the sky appears blue in color? The reason behind that is scattering, right? So one of the fine examples of scattering of light is that sky appears blue. Let us read something. The interplay of light with objects around us gives rise to several spectacular phenomena in nature. We know that very well. The blue color of sky, right, which you can see behind this, the blue color of sky, the color of water in deep sea. Yes, on the surface, the color of the water is generally bluish in nature, right? But in the deep sea, we know that color is different. Like this, this is an image of deep sea, right? Pretty dark blue or dark gray shade we can see over here in the deep sea. The color of the water is different than the surface. The reason behind this is again scattering of light. You can see the path of light is visible over here, right? This path of light is visible. This is also known as Tyndall effect, and Tyndall effect is also ultimately nothing but scattering of light. Apart from that, the reddening of the sun at sunrise and sunset. You know, when you observe the sun during day, the sun appears white or sometimes yellowish. But sun at the time of sunrise and sunset appears reddish. Now question is, why does this happen? Sun तो सेम જ છે, બરાબર ને? એ તો જ sun છે. The same sun appears white or yellowish during the day, and at the time of sunrise and sunset, we very well know that it appears reddish or sometimes mild orange in color. Why does this happen? The reason again is scattering of light. So these are some of the examples. No, the color of sky appears blue, the color of water in the deep sea, the reddening of the sun at sunrise and sunset are some of the phenomena that we see around us, and what is responsible behind all this is scattering of light. Now what is the reason behind scattering of light? Right, you know, this scattering is occurring in the atmosphere. What do we mean by scattering at a smaller level? Let us see something regarding that. Now it is written over here. The path of beam of light passing through a true solution is not visible. Now this is taught to you in standard 9th. If you remember, there are three types of solution, you know. True solution, colloidal solutions, and suspension solution. I hope you remember this. When you pass a beam of light through true solution, the path of light is not visible. You know, the path of beam of light through a true solution is not visible. Right? It is not visible. But this path becomes visible when you pass it through a colloidal solution. Right? Now, the reason behind this is that in the true solution, the particles of solute are solubilized. The particle size is very much small that we cannot see them with naked eyes. But in case of colloids, the particle size is bit larger. And whenever a light strikes this, the light is scattered. So one thing is sure that in order to get scattering, the particle size should be a bit more. If the particle size is very small, scattering is not possible. For scattering, you need particles. Right? See, this is the example of light passing through true solution, colloidal solution, and suspension solution. We can see whenever this light is passing through the true solution, the path of the light is not visible. So this is a true solution, while this is a colloidal solution and this is a suspension solution. Now when light passes through colloidal solution, you can see over here the path of the light is visible. You can see in a much clearer way the path of the light is visible over here. Why path of the light is visible over here? Because light interacts with the particles, because the particle size over here is more. Here the particle size is so much less that the light cannot easily interact with them. Here the light strikes the particle and gets scattered. Light फैला इच्छा बराबर ना. Hence we can see the path of light. I hope this is quite clear to you. Right. Now let us study what is Tyndall effect. Almost similar to scattering, but in a broader manner. Let us study. The Earth's atmosphere is a heterogeneous mixture of minute particles. See, the word used over here should remind you of something. Heterogeneous mixture. Do you remember colloids? Colloids are actually heterogeneous, but they appear like homogeneous. I hope you remember this. Colloids are actually heterogeneous, but they appear like homogeneous. So same is the example of our Earth's atmosphere. The Earth's atmosphere is a heterogeneous mixture of what? Of minute particles. You know, Earth's atmosphere has many things. Earth's atmosphere has molecules of air. Different gases are there, like suppose nitrogen is there, oxygen is there, carbon dioxide is there. Different gases are present. Then what is present in Earth's atmosphere? Smoke. Smoke is present in Earth's atmosphere. Then tiny water droplets. Tiny water droplets are present. Then suspended particles of dust are also present. Particles of dust are also present. So you can see a variety of particles are available over here. Right, the molecules of gas are there, molecules of water vapor are there, smoke is there, particles of dust are also there, variety of particles are there. Now whenever light, actually sunlight, because in our atmosphere which light passes? Sunlight passes. So sunlight will interact with these particles and the sunlight gets scattered. This scattering of sunlight due to these particles is known as Tyndall effect, and also known as scattering of light. And this is a very important point to discuss. When a beam of light strikes such fine particles, the path of the light becomes visible. This is called scattering of light. See, this is very much important. The path of the beam of light becomes visible. This phenomenon is known as scattering of light. So there are many particles over here. Light comes from here, but we cannot see it. But when it strikes with the surface, then we can see the path of light. And when we see this path of light, it is become visible to us. And this phenomenon is known as scattering of light. I hope this is clear to you. All of you are now clear with what do we mean by scattering of light. We cannot see light in general, but Due to striking of the light with some small particles present in the atmosphere around us, we can see the path of light. This effect is known as scattering of light. The light reaches us after being reflected diffusely by these particles. The phenomenon of scattering of light by colloidal particles gives rise to Tyndall effect. So scattering of light is in general for all the types of solutions or particles. But if this scattering of light, right, the scattering of light is done by colloidal particles, it gives rise to Tyndall effect. Examples of Tyndall effect: when a fine beam of sunlight enters a smoke-filled room through a small hole, the Tyndall effect is observed. See, I will display an image for this rather than explaining. See, this is a dark room, and you can see from a small window sunlight is coming inside. Outside this window we cannot see the path of sun rays or sunlight, but inside, due to Tyndall effect, now you can see these rays. Right, you can see the direction of it. So now the path of these rays is visible to you. You know the path of light now. This is known as Tyndall effect. This is the best example of Tyndall effect. Right? Another example. Tyndall effect can also be observed when sunlight passes through a canopy of dense forest. Here tiny water droplets in the mist scatter the light. See, inside the room smoke or dust act as fine particles. In the forest, water droplets act as fine particles. See, this is again Tyndall effect. I hope you have experienced this once in your life somewhere. Right. See, this is a forest. This is the sun, and sun rays are coming over here. Actually, we cannot see the sun rays or sunlight, but here, inside the forest, you can see effect like this. We can see that the path of light is visible to us. This effect is again known as Tyndall effect. So I hope two things are very much clear to you: scattering of light and Tyndall effect. Scattering of light means the path of light becomes visible to us after the light interacts with the small particles in the atmosphere. And if those small particles are colloidal in nature, then that specific effect is known as Tyndall effect. I hope this is clear to you. Let us now move ahead and see some important aspects regarding the scattering. This is very much important to understand. If we don't understand something from here, you will not be able to understand the further topics, which are why the sky appears blue, why sky appears blue, why sky does not appear blue to the astronauts, why cloud appears white, why we use red as the danger signal, right? Why we see the sun to be reddish at the time of sunrise and sunset. The answer to all these questions is simple. All of this happen due to scattering of light. But friends, scattering of light itself is a broad phenomena. Before studying these topics, we have to throw some more light on scattering of light, like what is responsible for scattering light, what controls the scattering of light. We have to study this. So let us first discuss about it, some few points about scattering of light. Please pay complete attention over here. So now let us first focus on the 3 points that are given over here on our screen. The color of scattered light depends on the size of scattering particles. Yes, the scattered light will have some color, and the color of scattered light depends upon the size of scattering particles. So number one, I will write over here size of, oh, this is not a good handwriting. Let me write over here again. Number one, size of scattered particles. Size of scattered particles. Second, Very fine particles scatter mainly blue light, while particles of large size scatter light of longer wavelengths. So again, this same point gets repeated over here. If size of the scattered particles is very much small, they will scatter generally the light of blue color, and if the particle size is large, it will scatter generally light of longer wavelengths, which is generally red. And if the size of scattering particles is yet large, the scattered light may even appear white. So if the particle size is yet large, the scattered light may even appear white. So these 3 points explain us a single thing, that the color of the scattered particles depends upon the color of the scattered light depends upon the size of the particles, right? Size of scattering particles which are present in the atmosphere. Fine. If the particle size is less, they will generally scatter the light of smaller wavelengths, which is generally blue in color. If the particle size is large, they will scatter the light of red color, and if it is yet large, they may also scatter the light of white color. Second thing which is not mentioned over here, but I would like to mention, is distance. Right. If the scattered light has to travel long distance or has to travel short distances. If it has to travel long distances, we will get the scattered light of the colors which are having larger wavelength. So if I want my scattered light to travel long distances, that color will be having a larger wavelength, for example red color. And if the distance is short, we require the colored light of less wavelength, which are generally bluish in nature, and if the distances are more short, it can be white also, because there is not enough scattering. So now, speaking in our common language, scattering માટે આપણે હજી એક નવો શબ્દ વાપરી લઈએ, ફેલાવો. લાઇટ કેટલી ફેલાય છે અને કોના દ્વારા ફેલાવવામાં આવી રહી છે, આ બે વસ્તુ ઉપર ઘણી બધી વસ્તુ નિર્ભર રહે છે. ફાઇન. So I have spoken this in common language for a better understanding. Now let us see, sorry, a small illustration and animation for a better understanding. Suppose there is a scattering particle. Suppose this particle is present in the atmosphere and it will suppose scatter light. Now suppose light is incident on it. Now this is white light. What is it? White light or sunlight. Now we very well know that the white light or sunlight is made up of 7 colors. You can observe 7 colors over here: Vibgyor, violet, indigo, blue, green, orange, yellow and red. Right, you can observe those colors over here. So this is white light, combination of 7 colors. But you cannot see these 7 colors now. You can see them as white light only. Why? Because they are not splitted. They are not scattered. Now, this white light, when it is incident on some particle which is suspended in the atmosphere, this white light will scatter. And this is what I mean by scattering. The white light is scattering. You can see it is now split into 7 different colors. Right? This white light, it is combined. When it strikes the particle, it gets scattered, but it gets scattered into different colors. Now you can see violet, indigo, blue, green, yellow, orange, red, Vibgyor. Right? Yellow, orange and red. See, why I am showing you this animation is, many things will be clear from this. You can see here the wavelength is less. Wavelength is more, 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 again wavelength is more. So violet color is having the least wavelength, red color is having the most wavelength. So when I go from violet, indigo, blue, green, yellow, orange to red, I know that here the wavelength, it is indicated by lambda, is less, and here the wavelength is more. The wavelength increases when I go from here to here. So now what can I say about violet, or what can I say about the colors from violet, indigo and blue side, that their wavelength is generally less and these colors generally have more wavelength compared to these three. So now as their wavelength is less, I can write about them that such light will be scattered by small sized particles. If particle size is less, we will see scattering of these colors. If particle size is more, we will see scattering of these colors. Fine. If light has to travel shorter distances, this will be scattered. If light has to travel longer distances, this will. I hope this animation is clear to you. Fine. Let us now move ahead and see some individual examples, but this figure you have to keep in mind that this is white light composed of 7 colors, and whenever it is incident on a particle which is suspended in atmosphere, we get our 7 colors over here. Each of them is having different wavelength. So based upon their wavelengths, they will be traveling different distances. They will be scattered differently due to difference in their wavelengths. I hope this is clear to you. Let us now move ahead and see why is the color of clear sky blue. Fine, why is the color of clear sky blue? So now let us understand why the sky appears blue. Fine. See, this image represents us why the sky appears blue. First of all, I will explain you from this. See, this is sunlight. This is the outer space. This is earth. And this gap over here represents the atmosphere. Now what happens is the sunlight will emit the sun rays. This is actually the white light, the band of 7 colors. But we do not see different colors over here. This is now a single color. Now it travels through the outer space. Here we don't have more particles. So here there will be no scattering. And due to this reason, the sky is black at about more than 20 miles above the surface of Earth, which means that in the outer space the sky is black because the particles are not present over there, and hence there is no scattering. But once this light enters the atmosphere of the Earth, inside the atmosphere of the Earth there are many particles. Particles, for example, we have different gases, we have dust particles, we have water vapor, etc. Now out of this, majoritarily there are gases present in the Earth's atmosphere, because atmosphere is the mixture of gases, and these gases have very small particle size. Very small particle size. So now just consider that here we are having the sun, here we are having earth, surrounding the earth we are having atmosphere, and in the atmosphere we are having some small suspended particles, and the sun rays hit this particle and they scatter the light. But we are having 7 colors over here with GR. Now as the particle size is less, the light, the colored light which is having less wavelength will be scattered the most. So violet, indigo and blue will be scattered the most, while green, yellow and red will not be scattered up to that level. So violet, indigo and blue scatter मतलब ફેલાશે. કઈ light વધારે ફેલાશે? Violet, indigo અને blue color ની light વધારે ફેલાશે. But sun જ્યારે અહીંયાથી light rays નાખે છે બહાર, તો એની અંદર blue color નું proportion વધારે હોય છે. The color of blue, the proportion of blue colored light is more. Apart from that, our eyes are more sensitive to blue color. તો ફેલાય છે આ ત્રણે ત્રણ, વાયોલેટ, ઇન્ડિગો અને બ્લુ. બટ બ્લુ ની ક્વોન્ટિટી વધારે છે નેચરલી, અને અપાર્ટ ફ્રોમ ધેટ આપણી આંખો બ્લુ કલર થી વધારે સેન્સિટિવ છે. ડ્યુ ટુ ધેટ રીઝન the blue color gets scattered in the atmosphere, and hence we feel that the color of the sky is blue because the blue color is scattered. સૌથી વધારે blue color ફેલાય છે. I hope this is quite clear to you. Now let us read what is given in the textbook. The molecules of air, right? Molecules of air means different gases, and other fine particles in the atmosphere have size smaller than the wavelength of visible light, right? Or in short I can say the particle size is small, so they will definitely scatter the light which is having small wavelength. They scatter the light of shorter wavelengths at the blue end more effectively than the light of longer wavelengths at the red end. બરાબર છે? They scatter the light of shorter wavelengths at blue end more effectively. બધી લાઇટ સ્કેટર થશે એવું નથી કે રેડ કલરની લાઇટ સ્કેટર નહીં થાય, બટ સ્કેટરિંગ વધારે કોનું થશે? જે લાઇટ બ્લુ સાઇડ છે, મતલબ વાયોલેટ, ઇન્ડિગો અને બ્લુ, આ ત્રણેયનું સ્કેટરિંગ વધારે થશે compared to green, yellow, orange and red. The red light has wavelength about 1.8 times greater than blue light. Red light ની wavelength blue light કરતા 1.8 times વધારે છે. This is an important 1 mark question. Thus, when sunlight passes through the atmosphere, the fine particles in the air scatter the blue color. The fine particles in the air scatter the blue color more strongly than red. Clear છે? Sunlight is passing. When it enters the atmosphere, it will strike these particles. These particles will scatter the light of all the colors, but they will more effectively scatter the light of blue color because blue color is having shorter wavelength and this particle size is also small. So blue color gets scattered. Scattered मतलब blue color ફેલાય છે. એટલે બધી બાજુ આપણને blue color દેખાય છે. The scattered blue light enters our eyes, hence the color of sky appears blue. I hope this reason is clear to you. So here distance is not of that much of importance. What is of importance is the particle size of the particles that are present in the atmosphere. Of the particles that are present in the atmosphere. I hope this is quite clear to you. Why color of sky appears blue? Simply, the sunlight is composed of 7 colors. This sunlight enters the Earth's atmosphere and interacts with the different particles present in the atmosphere. When it interacts with the particles, it will scatter its 7 colors. But out of the 7 colors, those colors will be more scattered whose wavelength is less. Such colors are generally on the blue side, violet, indigo and blue, and out of which blue appears because naturally the proportion of blue color is more and sensitivity of our eye towards the blue color is also more. Hence we feel that the sky is blue. But actually the sky has no color, it is black. Fine. So when you are inside the atmosphere, you feel that sky is blue. When you are outside the atmosphere at very much higher altitude, for example, those astronauts who are in space, they see that color of sky is black because there is no scattering of light easily compared to the atmosphere that is over here. When you are on higher altitudes, you feel that the color of sky is black simply because there is very less scattering of light. I hope this is quite clear to you. See, it is written over here. If the earth had no atmosphere, there would not have been any scattering. Then the sky would have looked dark, or we mean that the sky would have looked black. I hope this is quite clear to you. This is a very important question from examination point of view. Let us now see why the danger signal lights are kept red in color. Again, the reason behind them is scattering of light. Scattering of light. But the aspect over here is different. In the previous one, the aspect was the particle size. Here the aspect is how much distance does the light has to travel. How much distance does the light has to travel? Based upon that, we will focus on why the danger signal lights are kept red in color. Let us see. The red light has larger wavelength and hence it is least scattered by fog or smoke. Now, this is a very important sentence as far as the explanation is considered. The red light has larger wavelength and hence it is least scattered by fog or smoke. Now, see, the fog or the smoke, their particle size is less. Fine, and hence they will scatter the light which is having smaller wavelength. But the red light is having larger wavelength and hence its scattering will be the least. મતલબ scattering will be least એનો meaning શું છે? કે એનો ફેલાવો ઓછો થશે. It means that the red light is able to travel longer distances. The red light is able to travel longer distances. એ ફેલાતું નથી. It is least scattered. એ ફેલાતું નથી, નહીં તો એની આજુબાજુનું અપિયરન્સ બધું રેડ લાગશે. એ તો એટમોસ્ફિયર રેડ લાગવા માંડે એવું છે. બરાબર ને? બટ હિયર ઇટ ઇઝ લીસ્ટ સ્કેટર્ડ. એ ફેલાતું નથી. જ્યાં છે ત્યાંનું ત્યાં જ રહે છે. Due to this, it is able to travel longer distances. Please don't confuse this with the blue color of the sky. In case of blue color of the sky, the blue light is scattered. So, blue light is scattered like this in atmosphere and hence we see this much portion of the sky to be blue or the entire sky to be blue. But here in this case, red light is not scattered. Fine, due to which it is able to travel longer distances. Let us study this. Therefore, it can be seen in the same color at a distance. Yes. એનો ફેલાવો નથી થતો. તો જે વસ્તુ રેડ છે એ રેડ જ દેખાશે કારણ કે રેડ કલર બહુ લાંબા ડિસ્ટન્સ ટ્રાવેલ કરી શકે છે. Hence, danger signal lights are kept red in color so that they are visible up to long distances. ગમે ત્યાં આપણે ડેન્જર રિપ્રેઝન્ટ કરવું છે, ટ્રાફિક લાઇટમાં આપણે રેડ કલર સ્ટોપ માટે યુઝ કરીએ, ઓર ગમે તે જગ્યાએ એમ્બ્યુલન્સ છે એની ઉપરના સાયરનનો કલર રેડ હોય, જ્યાં બી કોઈ ડેન્જર સિમ્બલ હશે, that will be generally of red in color because red color is visible to longer distances. એની જગ્યાએ બીજો કોઈ કલર રાખવામાં આવે તો એને દૂરથી જોવામાં તકલીફ થાય. એને દૂરથી જોવામાં તકલીફ થાય. મસ્ત એનિમેશનથી સમજાવું છું. Try to understand. Suppose these are two colors. આપણે અહીંયા ઊભા છીએ, સપોઝ કોઈ અહીંયાથી જોઈ રહ્યું છે અને એની સામે બે કલર છે, એક તો કંઈક બ્લુ કલરનું છે ને બીજું કંઈક રેડ કલરનું છે. હવે આ સમજો, આ સન નથી. જો આ સન હોત ને તો આની અંદરથી વ્હાઇટ લાઇટ નીકળત જે 7 કલરની બનેલી છે. આ તો બ્લુ કલરનું છે તો એની અંદરથી બ્લુ કલરની લાઇટ નીકળશે. આ રેડ છે તો આની અંદરથી રેડ કલરની લાઇટ નીકળશે લાઈક ધીસ. આમાંથી બ્લુ, આમાંથી રેડ. યુ કેન કમ્પેર. આની વેવલેન્થ ઓછી છે, આની વેવલેન્થ વધારે છે. રાઈટ. નાઉ દે આર ટ્રાવેલિંગ થ્રુ ધ એટમોસ્ફિયર. તો એટમોસ્ફિયરની અંદર તો ફોગ અને સ્મોકના પાર્ટિકલ્સ હશે. આ સપોઝ ફોગ ઓર સ્મોકના પાર્ટિકલ્સ છે. હવે અહીંયા વ્હાઇટ લાઇટ ઇન્સિડન્ટ નથી, અહીંયા શું છે? બ્લુ લાઇટ ઇન્સિડન્ટ છે. તો બ્લુ લાઇટ સ્કેટર થશે. Blue light will be effectively scattered. Why? The particle size of fog or smoke is less and they are able to scatter the light which is having less wavelength. So the wavelength of blue colored light is less and hence it is scattered. તો અહીંયા blue color ની light ફેલાઈ જાય છે. એ બહુ દૂર સુધી પહોંચી શકતી નથી. Viewer અહીંયા ઊભો છે, બરાબર ને? બટ એને આ બ્લુ કલર ઇફેક્ટિવલી નહીં દેખાય. જેટલી ઇફેક્ટિવનેસ થી તમને રેડ કલર દૂરથી દેખાઈ જશે એટલી ઇફેક્ટિવનેસ થી તમને બ્લુ કલર દૂરથી નહીં દેખાય. વાય? બ્લુ કલર ફેલાઈ જાય છે. હું બહુ લાંબા ડિસ્ટન્સની વાત કરું છું, 1-2 મીટરની વાત નથી થતી, બરાબર ને? 800-900 મીટર, 1 કિલોમીટરની વાત થાય છે. જે તમે 1 કિલોમીટર દૂર છો કોઈ વસ્તુથી અને તમારી સામે કોઈ વસ્તુ બ્લુ કલરની છે અને રેડ કલરની છે, તો રેડ કલર તમને ઇફેક્ટિવલી દેખાશે, બ્લુ કલર બી દેખાશે બટ રેડ જેટલો ઇફેક્ટિવ દેખાશે નહીં. વાય? Between you and this blue color there are many particles. These particles are smaller in size and they will scatter the light of small wavelength. હવે અહીંયા શું છે? અહીંયા તો રેડ કલર છે તો એમાંથી રેડ કલરની લાઇટ નીકળશે જેની વેવલેન્થ વધારે છે. આની વેવલેન્થ વધારે છે અને આની પાર્ટિકલ સાઇઝ ઓછી છે તો આ ભાઈ આનું સ્કેટરિંગ કરી શકતા નથી. ઓર જેટલું બ્લુ નું સ્કેટરિંગ કરી શકે છે એટલું રેડ નું સ્કેટરિંગ નથી કરી શકતા. ડ્યુ ટુ this light will travel further with the least effect of scattering, અને એ દૂર સુધી ટ્રાવેલ કરવાની ક્ષમતા ધરાવે છે. તો આપણે હવે અહીંયા ઊભે ઊભે જોતા હોય તો આપણને રેડ કલર આપણા સુધી પહોંચશે, બટ બ્લુ કલર આપણા સુધી પહોંચતા પહેલા ફેલાઈ જશે. દેખાશે એવું નથી કે નહીં પહોંચે, દેખાશે, બટ જેટલી ઇફેક્ટિવનેસ થી રેડ પહોંચશે એટલી ઇફેક્ટિવનેસ થી બ્લુ પહોંચશે નહીં. See, this is not maths that 2 plus 2 will be 4. Right? There are some conditions, there are some reasons, and there are some approximations also. આમાં પછી અમુક લોકોનો મને ડાઉટ માટે ફોન અને મેસેજ આવશે, સર તો એવું હોય કે બ્લુ કલર અને રેડ કલર બંને આપણાથી 2 કિલોમીટર દૂર હોય તો બ્લુ દેખાય જ નહીં અને રેડ આપણને દેખાય. એવું હું નથી બોલ્યો. હું શું કહું છું, જેટલી સહેલાઈથી તમને રેડ દેખાશે એટલી સહેલાઈથી બ્લુ નહીં દેખાય. વાય? બ્લુ નું સ્કેટરિંગ થઈ જાય છે, રેડ નું એટલું બધું સ્કેટરિંગ થતું નથી. બ્લુ ફેલાઈ જાય છે, રેડ ફેલાતો નથી. ઇટ ઇઝ ટ્રાવેલિંગ લોંગર ડિસ્ટન્સીસ. સમજાય છે? તો જ્યાં બેકગ્રાઉન્ડ ની વાત આવે, જ્યાં ફેલાવાની વાત આવે ત્યાં બ્લુ કલર દેખાશે. ફોર એક્ઝામ્પલ સ્કાય, તો સ્કાય બહુ બ્રોડ રિજિયન છે, ત્યાં બ્લુ કલર ફેલાય છે એટલે આપણને એન્ટાયર સ્કાય બ્લુ લાગે છે. સમજાય છે? બટ ટ્રાફિક લાઇટ ત્યાં રેડ કલર, હવે જો રેડ કલર ફેલાઈ જાય તો ટ્રાફિક લાઇટ ની આજુબાજુનો બધો એરિયા મને રેડ કલર ફેલાઈ જાય તો દેખાવાનો નથી ને. મારે તો એ એક્ઝેક્ટ સ્પોટ ને રેડ જોવો છે, તો એ લાઇટ ફેલાવવી ન જોઈએ, બલ્કે આપણા સુધી ટ્રાવેલ કરવી જોઈએ. બરાબર ને? એના લીધે આપણે એવો કલર સિલેક્ટ કરીએ છીએ જે આપણને દૂર સુધી દેખાય. ફાઇન. I hope this is quite clear to you. So this is the reason why danger signals are generally kept red in color, because of its larger wavelength, and because of its larger wavelength its scattering will be very much less. I hope this example is clear to you. Let us now study the final point, why sun appears reddish at sunrise and sunset. Why sun appears reddish at sunrise and sunset. So why sun appears reddish at sunrise and sunset? See now, from this word reddish we can just understand that here again the story will be about distance. How much distance does the ray has to travel rather than the particle size. And somewhere I have created a very beautiful animation by which once again it will be clear to you why the sky appears blue and the sun inside it appears reddish at sunrise and sunset and white during the day. Everything will be clear from this animation. I hope you like this. So the question is, why sun appears reddish at sunrise and sunset? We very well know this, right? Sun appears reddish at the time of sunrise and sunset. Why? Let us see. Suppose this is the surface of the earth and here we have horizon, the place. If sun is below this and if sun rises above, it is known as sunrise, and if sun is here and it goes below, then it is sunset. Right? Suppose we feel that sun is over here. Suppose at the time of sunrise sun was here and now it is coming here, then this sun will appear reddish. Why? Let us see this. We are suppose observing from here, right? We are so much curious, we are thinking, why is the sun appearing reddish when it is over here at the horizon? See, at the time of sunrise the sun is at the horizon, right? The sun is at the horizon, so sun will emit sunlight, and we very well know that the sunlight is made up of 7 different colors, right? Violet, indigo, blue, green, orange, red. They all travel together. Basically it is white light, but white light is made up of 7 colors. Now we very well know that when this is transmitted, these colors are having different wavelengths. These colors are having different wavelengths. Now they will enter the atmosphere of the earth. They will enter the atmosphere of the earth. First thing is that these rays will not easily reach the atmosphere of the earth, or if they reach, they will be scattered easily. Which ray or which color has the longest wavelength? Red one. So definitely till the time all the rays reach this fellow, the red will reach, but till then everything else will be scattered. The red light reaches the observer over here, but everything else gets scattered, right? Suppose these rays enter the atmosphere, right? And inside the atmosphere there are many small particles. These lights interact with the small particles and they scattered. As these particles are small in size, they scatter the blue light more effectively, while they are unable to scatter the light rays with longer wavelength light red. So what happens is blue light અહીંયા ફેલાઈ જાય છે એટલે આ બધું આપણને બ્લુ બ્લુ લાગે છે બટ રેડ લાઇટ ફેલાતી નથી. રેડ લાઇટ તો આપણા સુધી પહોંચે છે. રેડ લાઇટ તો આપણા સુધી પહોંચે છે. આઈ હોપ ધીસ ઇઝ ક્લિયર ટુ યુ. એટલે જ તમને સ્કાય પૂરેપૂરો બ્લુ દેખાય છે બટ લાંબો ડિસ્ટન્સ ટ્રાવેલ કરવાનો હોવાથી બીજા બધા કલર આપણી તરફ પહોંચી શકતા નથી. બીજા બધા કલર આપણા સુધી પહોંચતા પહોંચતા ક્યાંક ને ક્યાંક એટમોસ્ફિયરમાં સ્કેટર થઈ જાય છે અને રેડ કલરની વેવલેન્થ સૌથી વધારે છે. તો વી ફીલ ધેટ ધ સન અપિયર્સ રેડ. સો ડ્યુ ટુ ધીસ રીઝન ધ સન at the time of sunrise it is at horizon, at the time of sunset also it is at the horizon, it appears red. બહુ સીધી વસ્તુ છે. Why? Because from the horizon it has to reach us and the distance between us and this place is very much large, due to which only light rays which are having longer wavelength will reach us. Now let us think vice versa. Let us think that why sun appears white during the day or yellowish during the day. See, during the day the sun has to rise. It will move from here to here. Sorry, I will play it again. See, the sun will during the day come overhead also. આ સવારના 5:30 વાગ્યા છે બરાબર ને. સવારના 5:30 ભાઈ અહીંયા છે અને પછી દિવસ દરમિયાન 8, 9, 10, 11 અને 12 વાગી જશે તો સૂરજ એક્ઝેક્ટલી આપણી ઉપર આવી જશે. The sun will be overhead. Now what do you think? This distance is this much and from here the distance is this much. Which distance is longer? Definitely this distance is longer and this distance is smaller. So here the light rays have to travel a longer distance. Due to this longer distance all other colors get scattered, but red color is having large wavelength, it does not get scattered and enters our eyes, due to which the sun is red. But here the distance is smaller. The distance is smaller. So before reaching here, they have to travel a small distance. તો બધાનું હજી કોઈ ઇનફ સ્કેટરિંગ નથી થયું. બધી લાઇટ હજી ભેદી જ છે. કોઈ ડિફરન્સ નથી કે ભાઈ આણે વધારે ડિસ્ટન્સ ટ્રાવેલ કરી લીધો ત્યાણે ઓછો ડિસ્ટન્સ ટ્રાવેલ કરી લીધો. આ ડિસ્ટન્સ બહુ જ ઓછો છે. ડિસ્ટન્સ બહુ જ ઓછો છે તો આ બધી લાઇટોને ફેલાવાનો ચાન્સ મળતો નથી. ઇન્સ્ટેડ એ બધી એક સાથે જ છે અને જ્યારે આ સાતે સાત લાઇટ હજી છૂટી નથી પડી એની વચ્ચે વેવલેન્થનો ડિફરન્સ એટલો બધો નથી આવ્યો તો એ સાતે સાત ભેદી રહેશે and they will appear white. They will appear white because અહીંયા તો લાંબો ડિસ્ટન્સ ટ્રાવેલ કરવાનો છે. બહુ સીધી વસ્તુ છે. સપોઝ there is a running race of 10 people. 10 જણા રનિંગ રેસમાં છે અને આપણે રનિંગ રેસ રાખીએ ભાઈ 5 મીટરની. તો 5 જ મીટર તો કોઈ ડિસ્ટન્સ નથી ને. રૂમના એક છેડેથી બીજે છેડે જાવ તો 5 મીટર થઈ જાય. એમાં તમે વિનર સિલેક્ટ કરી શકો? ન સિલેક્ટ કરી શકો. તમને એમ જ લાગશે કે 10 જણા એક સાથે સ્ટાર્ટિંગ લાઈનથી ફિનિશિંગ લાઈન ઉપર પહોંચ્યા છે. વાય? તમે ડિસ્ટન્સ બહુ ઓછો રાખ્યો છે. એ આવડો કેસ છે. બટ તમે 5000 મીટરની રેસ રાખો તો એ તો લાંબો ડિસ્ટન્સ થાય બરાબર ને. તો એની અંદર અમુક લોકો શોર્ટ ટ્રાવેલ કરશે, અમુક લોકો લોંગ ટ્રાવેલ કરશે, અમુક થાકીને વચ્ચે ફેલાઈ જશે તો તમને ખરેખર વિનરની ખબર પડશે. બટ તમે ડિસ્ટન્સ રાખો 5 મીટર તો એમાં તો બધાય રાજા જ હોય. એમાં તો કોઈ ડિફરન્સ તમે પોઈન્ટ આઉટ કરી શકવાના નથી. હેન્સ all it feels that all of them remain together and if all of them remain together this will appear white. So during the day the sun appears white. So from this single animation we are able to know why the sky appears blue. Now outside the sky there is no scattering. So outside the sky or outside the atmosphere the sky will be black or dark. Inside the atmosphere the sky will be blue. At the horizon at the time of sunrise and sunset the sun appears red, but during the day it has to travel shorter distances and it appears white or yellowish in color. I hope this is very much clear to you. Let us now move ahead and see what is given in the textbook. At the times of sunrise or sunset, light from the sun near the horizon passes through thicker layers of air and larger distance in Earth's atmosphere before reaching our eyes. Near the horizon, most of the blue light and shorter wavelengths are scattered away by the particles. When sun is at horizon, majority of the blue light and shorter wavelengths are scattered, due to which the sky appears blue. However, the light that reaches our eye is of longer wavelength, and this gives reddish appearance to the sun. બરાબર ને જે શોર્ટ વેવલેન્થ હતી એ તો સ્કેટર થઈ ગઈ, એ તો ફેલાઈ ગઈ, એના લીધે મને સ્કાયનો કલર બ્લુ દેખાય છે. બટ જે લોંગ વેવલેન્થ છે એ સ્કેટર નથી થતી, એ ફેલાતી નથી અને મારી આંખો સુધી પહોંચે છે, ડ્યુ ટુ વિચ આઈ ફીલ ધેટ સન અપિયર્સ રેડિશ. However, light from the sun overhead would travel relatively shorter distance. જ્યારે sun આપણી ઉપર આવી જાય છે overhead, at that time it has to travel shorter distances. So at noon, sun appears white, as only a little of blue or violet colors are scattered. બધી લાઇટનું ઇનફ સ્કેટરિંગ થતું નથી, કારણ કે ડિસ્ટન્સ બહુ શોર્ટ છે, તો એમ જ લાગે છે કે બધી લાઇટનો કલર હજી ભેગો છે, and when they are together they appear white because there is not enough scattering due to shorter distance. So this is the reason why the sun appears reddish at sunrise and sunset. Now, in order to justify this, there is a small scientific experiment also given in our textbook, right? This, first of all, you have to write in CW also. I will mention over here, you have to write this in CW, and there are two parts. This is one of two, right? This is the first part and second part is in the upcoming screen. Let us first understand this is an activity. Just to clarify that for longer distances we see red color, and for shorter distances we see blue color, right? Explain the activity showing reddish appearance for sun at sunrise and sunset while the sky appears blue. See what it is written. Place a strong source of white light at the focus of converging lens L1. See, this is first lens. Converging lens, it means it is a convex lens. And here we keep a source of light. For example, we keep a bulb, we keep a torch, such that it is at the focal point of this. Now, when the incident ray travels through the focal point, the refracted ray will travel parallel to the principal axis. We very well know this. So we will get a parallel beam of light over here, right? Simply, due to this reason, we are keeping this source of light at the focal point such that after converging, they will travel parallel to the principal axis, right? So we get parallel beam of light. Now this parallel beam of light is allowed to pass through this tank, right? Let us read. Allow the light beam to pass through a transparent glass tank containing clear water. So this is having clear water, H2O. This T for tank. These light rays are traveling through the water, clear water. Allow the beam of light to pass through a circular hole C made in a cardboard. See, this is a cardboard, there is a hole C, and out of many rays, only a few rays will be allowed to travel from here, just to sharpen the image. Here there is another lens. It is again a convex lens. And if the light rays enter parallel, they will get focused on the focal point. So this MN, right, is the screen, and we will place the screen such that it is present at the focal point of the lens L2. This is lens L1, right? And this is lens L2. Sure. Allow the beam of light to pass through a circular hole C made in the cardboard. Obtain a sharp image of circular hole on the screen MN using a second converging lens L2 as shown in the figure. So बहुत simple છે. અહીંયા તમે લાઇટ રાખેલી છે, આના ફોકલ પોઈન્ટ ઉપર એ લાઇટ અહીંયા આની ઉપર ઇન્સિડન્ટ છે, એના લીધે પેરેલલ રેઝ મળે છે. આ પેરેલલ રેઝ ટ્રાવેલ ક્યાંથી કરે છે? વોટરમાંથી. આ નાનકડા પાર્ટમાંથી આટલી જ લાઇટ રેઝ આગળ જવા દેવામાં આવે છે. અહીંયા ફરી પાછી એક લેન્સ છે. જો આ બધી રેઝ પેરેલલ હોય તો રિફ્રેક્ટેડ રેઝ બધી ફોકલ પોઈન્ટ ઉપર પાછી ભેગી થશે ને. MN ઇઝ અવર સ્ક્રીન. શું છે? સ્ક્રીન. ક્યાં આપણને આપણી ઇમેજ મળશે. હવે શું કરવાનું છે? ઇન ધીસ ક્લિયર વોટર we have to add 200 grams of sodium thiosulfate in 2 liters of clean water in the tank. તો આની અંદર ઓલરેડી વોટર છે કેટલું? 2 liters, અને એની અંદર આપણે હજી શું નાખવાનું છે? 200 grams of sodium thiosulfate. અને બીજું શું નાખવાનું છે? 1 to 2 ml of concentrated sulfuric acid to water. 200 grams sodium thiosulfate અને 1 to 2 ml concentrated sulfuric acid આટલું આપણે પાણીમાં નાખવાનું. તો રિએક્શન થશે, અને એ રિએક્શન થવાથી અહીંયા સલ્ફર બનશે. શું બનશે? સલ્ફર. Let us see now what happens. So now inside this microscopic sulfur particles precipitate in about 2 to 3 minutes. તમે પાણીની અંદર જેવું સોડિયમ થાયોસલ્ફેટ નાખશો તો 2 કે 3 મિનિટની અંદર સલ્ફર પાર્ટિકલ્સ will be formed. સલ્ફર પાર્ટિકલ્સ હવે અહીંયા સલ્ફરના પાર્ટિકલ્સ બની ગયા બરાબર છે. પાર્ટિકલની સાઇઝ બહુ જ નાની છે. પાર્ટિકલની સાઇઝ છે નાની. સપોઝ હું અહીંયા સલ્ફરના પાર્ટિકલ્સ ડ્રો કરું, right? These are small sulfur particles and their particle size is less. હવે તમે આ ટેન્ક ને ઉપરથી જુઓ, અહીંયા સામેથી જુઓ ઓર આની પાછળથી જુઓ, ત્રણ સાઈડથી જોવાની છૂટ છે. અહીંયા તો પેક છે બરાબર ને. તમે આને ઉપરથી જુઓ, આ બાજુથી જુઓ ફ્રન્ટથી ઓર પાછળની સાઈડથી જુઓ, તમને ત્રણેય સાઈડથી આ બ્લુ લાગશે. ઓલ્ધો સલ્ફરનો કલર બ્લુ નથી, સલ્ફરનો કલર બ્લુ નથી, બટ છતાં તમને આવડું આ ચારેય ત્રણેય સાઈડથી બ્લુ લાગશે. ફ્રોમ ધ થ્રી સાઇડ્સ યુ વિલ સી બ્લુ લાઇટ. વાય? પાર્ટિકલ સાઇઝ નાની છે અને અહીંયાથી તમે લાઇટ મોકલો છો તો ડ્યુ ટુ લેસ પાર્ટિકલ સાઇઝ blue color will be scattered because wavelength of blue light is small, wavelength of blue light is less, right? So here it is written, this is due to scattering of short wavelengths by minute colloidal sulfur particles. Particle size is less, so the light that will be scattered also its wavelength will be less, so blue light is scattered and we can observe it from three sides. નજીકથી જોઈએ તો. But if I see it from here, હું જો આ બાજુથી જોઉં, આના અંદરથી આ બાજુથી, તો મને આ રેડ કલરનું લાગશે. See, the color of the transmitted light from the fourth side of the glass tank facing the circular hole at first appears orange red and then bright crimson red color on screen. હું જો આ સાઈડથી જોઉં, if I see from this side, સામેથી જોઉં છું બ્લુ, પાછળથી જોઉં છું બ્લુ, ઉપરથી જોઉં છું બ્લુ, બટ હું જો આ સાઈડથી જોઉં તો ડિસ્ટન્સ વધી ગયો, અને ડિસ્ટન્સ વધી ગયો તો આ મને કેવું લાગશે? રેડિશ લાગશે, ઓરેન્જ લાગશે. તો અહીંયા રોલ કોનો છે? પાર્ટિકલ સાઇઝનો. પાર્ટિકલની સાઇઝ ઓછી છે તો એણે બ્લુ કલરની લાઇટ સ્કેટર કરી દીધી, બ્લુ કલરની લાઇટ ફેલાવી દીધી. તો નજીકથી જોઈશ તો મને આ બધું બ્લુ લાગશે બરાબર, બ્લુ કલરની લાઇટ ફેલાઈ છે. બટ ઇફ આઈ ઓબ્ઝર્વ ફ્રોમ હિયર, હું આ સર્ક્યુલર હોલમાં અહીંયાથી જોઉં છું તો ડિસ્ટન્સ વધી ગયો, અને લાંબુ ડિસ્ટન્સ કોણ ટ્રાવેલ કરશે? જેની વેવલેન્થ લાંબી છે. કોની વેવલેન્થ લાંબી છે? ઓરેન્જ અને રેડ કલરની. તો આ મને રેડ કલર જેવું લાગશે, અને એની જે ઇમેજ અહીંયા બનશે ને એ બી બ્રાઇટ રેડ કલરની હશે. So what is the conclusion? When light has to travel shorter distance, it is not completely scattered. બહુ ઇમ્પોર્ટન્ટ છે. When light has to travel shorter distance, it is not completely scattered, and light that reaches our eyes is of short wavelength, which is blue. When distance is short, what is the color received by our eyes? Shorter wavelength blue. But if the light has to travel longer distance, then shorter wavelengths are scattered. નાની wavelength વાળા તો scatter થઈ ગયા, ફેલાઈ ગયા. But the light that reaches our eye is of longer wavelength. તો જ્યારે distance લાંબો છે ત્યારે ઓછી વેવલેન્થ વાળું બધું ફેલાઈ જશે, અને જેની વેવલેન્થ વધારે હશે એ આપણી આંખો સુધી પહોંચશે. રાઈટ? This is very much important and you have to write this. રાઈટ? આ આન્સર ખૂબ જ ઇમ્પોર્ટન્ટ છે. This is part 1 of 2. Please pause the video and write this much, draw this diagram, and then after writing this much you have to write this also. This is part 2 of 2. Right? તો આની સિમ્પલ થિયરી સમજી લ્યો. If particle size is small or if distance is also small, then we will get blue colored. If distance is large, then we will get red color. Blue ફેલાઈ જશે અને red આપણને જોવા મળશે. Fine, so chapter is over. Now you have to write some question answers. I will play them one by one. This is page number 1. Pause the video and write this page number 1 in your CW. Fine, some of them we have written previously, but still check it out. Those which are remaining you have to write. These are all textual questions. Pause the video and write them in your CW. Moving ahead, this is page number 2. Pause the video and write this much down in your CW. Fine, then I will move ahead. This is page number 3. This question is also important for 1 mark. Why does the sky appear dark instead of blue to an astronaut? Because surrounding the astronaut there is no atmosphere. Fine, there is absence of atmosphere, and due to this there is no scattering, hence sky appears dark to the astronaut. Right? This is page number 3. Write this answer down. Then this is page number 4. Right? This was page number 3 and this is page number 4. These are some MCQs with answers given over here. They are quite simple. Fine. Just mark them down and write in your CW. Then we are having number 11. Right? This is a sum we will solve now. A person needs, first of all I will write over here, this is page number 5. Right? Now let us discuss. A person needs a lens of power minus 5.5 diopters for correcting his distant vision. For correcting his near vision, he needs a power plus 1.5 diopter. What is the focal length of the lens required for correcting the distance vision and the near vision? So we will write over here in answer. Right, we will write the solution over here. And we will write the first one. Focal length needed to correct distant vision. To correct distant vision. Right, so we will use the formula. P is equal to 1 upon F. Now power is already given to us for distant vision, it is minus 5.5. So I will write over here minus 5.5 is equal to 1 upon F. Again I can write minus 55 upon 10 is equal to 1 upon F. Now when I invert this, I can write minus of 10 upon 55 is equal to F. Fine. I hope this is clear to you. So we can write F is equal to minus 10 upon 55. Now both of them come in the table of 5. So 5 2s are, 5 11s are. So F is equal to minus 2 upon 11 meters. Minus 2 upon 11 meters. I hope this is clear to you. If you want to further simplify this, you can just take the decimals over here. Right? The answer of focal length will be always in meter. Now focal length is negative over here. So which type of lens it is? The lens is concave lens. Concave lens. Fine. So for distant vision, for correction of distant vision, we need concave lens. Similarly, we will do the second one also. For near vision, focal length for near vision. Again, we will use the formula P is equal to 1 upon F. P given is 1.5 is equal to 1 upon F. 1.5 can be written as 15 upon 10 is equal to 1 upon F. If I invert, this will be 10 upon 15 is equal to F. So we can write F is equal to 10 upon 15. 5 3s are, 5 2s are. So F is equal to 2 by 3. Now when you divide 2 by 3, you get 0.666 dot dot dot. Or cumulatively you can write plus 0.67 meters. So again the focal length over here is positive, so lens that is used will be a convex lens, because focal length of convex lens is always positive. So for distant vision we need a concave lens, for near vision we need a convex lens. I hope this is clear to you. Please pause the video and write this down in your CW. Moving ahead. Number 12. This is page number 6. This is a sum actually. The far point of a myopic person is 80 centimeters in front of eye. Now first of all I will mark this as important. Not from examination point of view, but from knowledge point of view as far as your maths is concerned. We will not move ahead of this line because these sums are very much confusing. The far point of a myopic person is 80 centimeters in front of eye. See, I will write something over here. First of all, the person is suffering from nearsightedness. the person is suffering from nearsightedness. So there are two things about that person. He or she is able to see nearby objects clearly. Nearby objects clearly. Fine. But he or she has problem to see the objects which are far. Right. So now problem is over here. There is problem to see far objects. So we can say that the far point is affected. The far point is affected. Now you have to again ask yourselves two questions, and based upon that you will get the value of u and v. Right? We will get asked two questions, and from that we will get the value of u and v. Far point is affected. So our first point is, how far can we see? How far can we see? We can see up to infinity. Right? We can see up to infinity. So that will be our object distance. That will be our object distance infinity. And here the far point is affected. And it is affected how much we can see. The far point of a myopic person is 80 centimeters in front of the eye. So here is the eye and the far point is 80 centimeters in front. So if I apply the Cartesian sign convention, here if it is the optical center, then this distance is on the left side. So this 80 centimeters will become our V. And we can write over here minus 80 centimeters. Now you have the value of U, you have the value of V. Simply apply the lens formula. After applying the lens formula, we will get the value of F. We can see the value of F is negative. It means that we will use a concave lens. And we very well know that, right? Concave lens will be used. Fine. To correct nearsightedness. Those who can see the nearby objects clearly, but they are not able to see the far objects. For them, we will use concave lens. So here the answer is in centimeter. We have converted this into meters. Right? And from that we have found the power, which is minus 1.25 diopters. Now this is very much easy. What is tough is this. Have to determine the value of U and V. That depends upon whether a person is suffering from myopia or hypermetropia. Because whenever a person is suffering from myopia or nearsightedness, his far point is affected. In case of hypermetropia, the near point will be affected and you have to assume the values like that. I think this is clear to you. But in case you still have doubt, rewind the video, watch it once again, or we will solve one more sum. Based upon that, it will be very much clear to you. Fine. For now, please pause the video and write this down. Also write this also down. Right. How much far we can see. Right. Based upon this, u is infinity and v is minus 80 centimeters, which is given to us. Sure. Please pause the video and write this down. Once you finish writing this, we will move to the next sum, sum number 13. And this is page number 7. This also you have to write in your CW. Make the diagram to show hypermetropia is corrected. See, now draw a normal diagram of hypermetropia. We already have done this. We will solve the sum. The near point of a hypermetropic eye is 1 meter. Now this is very much important. First of all, 1 meter is nothing but 100 centimeters. 1 meter is nothing but 100 centimeters. Now again see, I will write over here hypermetropia. Hypermetropia. Hypermetropia or farsightedness. Hypermetropia or farsightedness. So two things will be very much clear from this. Farsightedness means able to see far objects clearly. Able to see far objects clearly means there is problem in seeing nearby objects. There is problem in seeing nearby objects, which means that the near point of eye is affected. Near point of eye is affected. So standing here, we will ask two questions. Previously, the far point was affected. So we were asking how far can we see up till infinity. Now here near point is affected. So our question will be how much near can we see comfortably, or what is the near point of eye, that will be our object distance u, and we very well know that the near point of our eye is 25 centimeters, and applying the Cartesian sign convention the object distance will be always negative. Right, now this 25 is not at all given in question. At last it is given, assume that near point of normal eye is 25, but even if it is not given, object distance will be minus 25 centimeters. સિમ્પલ છે. ફાર પોઈન્ટ અફેક્ટ છે તો પૂછવાનું ભાઈ કેટલું દૂર જોઈ શકીએ, ઇન્ફિનિટી, તો આપણો ઓબ્જેક્ટ ડિસ્ટન્સ એ બની જશે. નિયર પોઈન્ટ અફેક્ટ થયો હોય તો આપણે પૂછવાનું ભાઈ કેટલું નજીકમાં નજીક જોઈ શકીએ છીએ કમ્ફર્ટેબલી 25 સેન્ટીમીટર સુધી, તો that will be our near point. Right, so again what will be our v? Our v will be given in the question minus 100 centimeters. The near point of hypermetropy is 1 meter, which is minus 100. Again apply the length formula, get the value of f. You can see f is 33.33 centimeters. Converting into meters, we get 0.33 meters. The answer is positive. The answer is positive. It means that we require a convex lens. Then we will find the power. P is equal to 1 upon f. So all these steps are very much simple. Everything lies on this. You should be very much clear about this. Fine. Please pause the video and write this down in your CW. Once, please write this also. This is very much important. Once you finish writing this, you have to write these value based questions. These are the extra questions that I have made. Please write them in your CW 1, 2, 3 and 4. This is page number 8. They are important for 1 mark question. Then this is page number 9. There are some fill in the blanks actually. See, this was page number 8 that you have to write. Right. Then page number 9. Solve them. Right, I have given options over here, and please ask while doing the message to me if you have any doubts. Right, these are simple fill in the blanks. Sure, please write them in your CW compulsorily. This is page number 9, and very much important, on page number 10 you will write this match the following. If you know this, then the chapter will be very much clear to you. Right, page number 10. You have to write this match the following. Like what is the function of retina, what is the correction of hypermetropia, options are given over here. Twinkling of stars, early sunrise, late sunset, what phenomenon is responsible, you have to write. Alright, so write this down in your CW, complete the CW. Fine, so today it's Monday, we have attended this video lecture. Fine, now you have to do homework, all question and answers one time. Your CW should be complete. Apart from that, you have to do the homework one time. This is very much serious. I have checked the homework of few students. Some of them are doing very much in a very much better manner, and some of them are not at all doing that, which is quite serious. You are still not taking this thing seriously. Fine, so this homework is one time, and you have to show me this homework before Wednesday. Wednesday before 6 p.m. Right, so today it's Monday. Tuesday we will have a break. You will have reading time. On Wednesday you have to submit me homework before 6 p.m. and on Wednesday at 6:30 p.m. we will have a test. Right, be very much clear. Tuesday is a break, Wednesday before 6 p.m. you have to submit the homework, and Wednesday at 6:30 p.m. we will take a test, and solution of the test will be made available at around 8:30 p.m. on Wednesday. Then we will carry out the further actions from Thursday. Alright, so thank you very much for listening. The video lecture was a bit long today, but that is fine. And take very good care of yourselves and everybody in your surroundings. Goodbye.